Welcome back, everyone, to AI.Code.Cast. Today, we're going to do a deep dive into a problem that's all about finding the best way to get things done efficiently. And you can think about it this way.
Okay.
You're working with this very minimalist text editor,
Okay.
the kind that just has two commands, copy all and paste. And you start with a single A on the screen, and your goal is to get to an n number of A's.
Right.
But the catch is that you want to do it in the fewest steps possible.
Yeah, what's really interesting about this challenge is that it makes us think beyond just randomly hitting paste, right?
Right.
It's a problem that kind of brings together string manipulation with a little bit of number theory.
Right.
And it pushes us to come up with a clever strategy.
Yeah, exactly. It's like, if you think about it like optimizing a repetitive task in real life.
Yeah.
Like, let's say you had to make 10 copies of a document.
Okay.
You could print one, then another, then another.
Yeah.
But that would take forever.
You'd be there all day.
So you'd probably make one copy and then use that to make more copies and so on.
Right.
It's about finding that efficient pathway.
Yeah. And in this two keys keyboard problem, that efficient pathway isn't always so obvious.
Right.
So let's start by thinking about how someone might approach this problem when they first see it.
Okay.
They see the A on the screen and they have copy all and paste. What's the most intuitive thing to do?
Well, I think most people would probably just start copying and pasting,
Yeah.
trying to get to that target number of A's as quickly as possible.
Yeah.
It's kind of a brute force approach, right? Just try every combination until you find the shortest one.
Exactly.
Yeah.
And for small numbers, like if you're trying to get to 3 or 4 A's, brute force might actually work okay.
Yeah.
But what happens when you need to get to, say, 20 A's or 100?
Then things start to get messy.
Exactly.
You would be sitting there forever trying all these different combinations,
Yeah.
hoping you find the most efficient one.
Yeah.
There's got to be a better way.
And there is. This is where things get really interesting.
Okay.
The key to solving this efficiently is in understanding how numbers are structured.
Okay.
Specifically, we need to delve into prime factorization.
Hold on. Prime numbers. How did those fit into copying and pasting A's?
Right.
I'm intrigued.
It might seem like a jump, but trust me, they're connected.
Okay.
Think about it this way. Every single number can be broken down into a unique set of prime numbers that you multiply together. It's like the DNA of a number, its fundamental building blocks.
Okay, I'm starting to see where this is going.
Okay.
So if we figure out the prime factors of our target number n, we can use that to guide our copy-paste strategy.
Exactly. Each prime factor represents doing a copy all and then a bunch of pastes in a row.
Okay.
Let's take an example. Say our target n is 12.
Okay.
We find its prime factors, which are 2 times 2 times 3.
So to get 12 A's, we'd use those prime factors as like our roadmap. So we would copy all, paste once. That's one of the twos. Copy all, again, paste once, the second two, copy all one last time, and then paste twice for the 3.
You got it.
Yeah.
And that gets us to 12 A's in the most efficient way possible.
Wow.
We're not wasting any steps
Yeah.
by copying and pasting more than we need to at any given point.
That's pretty slick. It's like we're taking this shortcut through the number by understanding its prime factors.
Now, before we jump into specific solutions using this, let's address a question that our listeners might have.
Okay.
Finding prime factors, isn't that computationally expensive?
Right.
Especially for large numbers.
Yeah, that's a good question.
Yeah, that's a great question. And it's a valid concern, but here's the good news. We don't need to find all the prime factors of a number up to n.
Oh, okay.
We just need to check up to the square root of n.
Wait, really? Why is that?
Okay, so think about this. If a number has a prime factor that's bigger than its square root,
Okay.
it must have another prime factor that's smaller than its square root.
Okay.
It's like a balancing act. Right.
Okay, I see. So even if our n is a really big number, we can still find the prime factors we need pretty quickly.
Relatively quickly, yeah.
Okay. But how do we use those prime factors to actually write a solution?
So there's a couple of ways we can do that.
Okay.
One common way is called the iterative approach.
Okay.
And it's like taking a step-by-step journey through those prime factors to build up our count of A's.
So if we were to think about this in pseudocode, what would that look like?
Okay, so imagine we have our target number n.
Okay.
We start a counter for our steps and set it to 0. Then we start going through prime numbers, starting with 2.
Okay, so we're checking if n is divisible by 2.
Exactly.
And if it is, what do we do?
If n is divisible by 2, we divide n by 2, and we increase our step counter by 2.
Okay.
Remember that each prime factor means a copy all and at least one paste.
Got it. So we keep dividing in by 2 and increasing the counter until it's not divisible by 2 anymore.
Exactly.
What happens when we get to a number that's not divisible by 2?
Then we move on to the next prime number, which
Okay.
is 3. And we repeat the process, check if n is divisible by 3, divide it if it is, and increase our counter.
And we just keep doing that.
Keep going.
Going up the prime numbers until n becomes 1.
You got it.
I-
Once n is 1, we've accounted for all the prime factors,
Yeah.
and our counter will have the minimum number of steps it took to get to NAs.
Okay. That's pretty easy to follow.
Yeah,
It's like systematically breaking it down
Uh-huh.
and using that to guide our copy and paste actions.
exactly.
But what about another approach? I've heard about recursive solutions for this problem too.
Yeah, recursion is a really cool technique where a function basically calls itself.
Okay.
It breaks a problem down into smaller pieces that look like the original problem.
Okay.
It's kind of like when you look in a mirror
Mhm.
and it's reflecting another mirror and you see this infinite chain of reflections.
Whoa, that's a little mind-bending.
Yeah, it's a little trippy.
How does that apply to our 2-keys keyboard problem?
Okay, so let's say we have our target.
Okay.
In a recursive solution, the first thing we do is find the smallest prime factor of n.
Okay.
Let's say it's 2.
Okay, so we find that prime factor. What do we do with it?
We would increase our step counter by 2
Okay.
to represent a copy all and a paste for that prime factor. And then here comes the magic.
Okay.
We call the same function again,
Okay.
but this time with a new target
Right.
and divide it by that prime factor.
So in our example where Shannon was 12,
Yeah.
we find the prime factor 2, we increase our counter,
Mm-hmm.
and then call the function again with 612 divided by 2.
Exactly.
Oh, yeah.
And inside that recursive call, we repeat the process, find the smallest prime factor of 6, increase the counter, and call the function again with 3.
Okay.
And this keeps going until we hit what we call the base case.
And the base case is when our target is reduced down to 1.
Yes.
That's when we know we're at the end.
Exactly.
Okay.
At that point, our step counter has the total number of operations, which is the fewest steps to get to N and A's.
Okay.
It's like we've unraveled the problem step by step.
That's pretty elegant.
Yeah.
I have to admit, recursion can sometimes feel like magic.
It does. A little bit.
Is there a way to picture it or understand it better?
Think of it like building a tower with Lego bricks.
Okay.
Each time we call the function again, it's like adding a new layer of bricks.
Okay.
And each layer represents the actions we take for a prime factor.
Okay.
And we keep adding layers until we reach the height we want, which is our target number, n any.
Okay, that helps. It's like we're breaking down this big task into smaller, more manageable ones.
Exactly.
But I've heard that recursion can sometimes be slow
Yeah.
and use up a lot of resources.
Yeah.
Is that something to worry about here?
That's a good point. Recursion can lead to doing the same calculations over and over again if we're not careful.
Yeah, it's like taking the scenic route when there's a much faster way to get there.
Right. A faster way.
Yeah, and to avoid that, we can use this really cool optimization technique. It's called memorization.
Memorization. Okay.
Yeah, it's basically just remembering the results of calculations we've already done.
So it's like having a cheat sheet where we store the answers to those smaller problems we've already solved.
Exactly. We create a lookup table
Okay.
where we keep track of the minimum steps needed for each and each one we come across during our recursive calls.
Okay.
And if we see the same n, we don't have to recalculate it.
Gotcha.
Just grab the answer from our table.
That's a really smart optimization. It's like cutting out all those unnecessary detours.
Yeah.
So we've talked about two main approaches, the iterative way and the recursive way with memorization. How do they compare in terms of efficiency?
So both methods get us to the same goal,
Okay.
and they both use prime factorization.
Right.
In terms of how long they take, they're pretty similar.
Okay.
The iterative way takes roughly the square root of n steps,
Okay.
and the optimized recursive approach has about the same complexity.
So there's no clear winner when it comes to speed.
Not really. So it sounds like the choice might depend on things like coding style or what the programmer prefers.
Yeah, absolutely. Some programmers like the iterative approach because it's straightforward and easy to understand. It's like following a recipe step by step.
Right.
Others prefer the elegance of recursion, especially with memorization.
Yeah.
It can make the code shorter, and it reflects the way the problem itself is structured.
It's like choosing between a well-organized factory and a beautifully crafted, intricate machine.
Exactly.
Both get the job done,
Yep.
but in different ways.
Yeah, the choice really depends on the situation,
Right.
the programmer style, and the specific needs of the project. But the key takeaway here is that understanding prime factorization gives us a really powerful way to optimize this problem.
Yeah, it's fascinating how a concept from math can be used for something like copying and pasting text. It
Yeah,
really shows how connected different areas of math are.
it does. And it reminds us that sometimes the most creative solutions come from looking at things from a new angle.
Absolutely. Before we wrap up, can you tell us a little bit more about how this problem relates to dynamic programming?
Yeah, so dynamic programming is a technique where you solve a problem by breaking it down into smaller, overlapping subproblems,
Okay.
and then you store the solutions to avoid redundant calculations.
Okay.
Think of it like building something with Legos.
Mm-hmm.
You use the bricks you've already put together to support the new ones.
So even though we didn't specifically call our solutions dynamic programming,
Right.
the main ideas are still there.
Exactly. The idea of breaking down the problem and remembering the solutions is at the heart of dynamic programming.
Okay.
In this case, our smaller problems involve finding the minimum steps for smaller in values,
Gotcha.
and memorization helps us avoid repeating those calculations.
That's a great point. It shows how even seemingly easy problems can connect to bigger algorithmic ideas.
Yeah.
Now, as we finish up, what's one final thought for our listeners?
The next time you run into a problem that feels really hard,
Mm-hmm.
remember this two keys keyboard problem. Ask yourself, can I break it down into smaller pieces?
Right.
Could understanding how the problem is structured help me find a better solution?
It's about looking for those hidden shortcuts and opportunities to make things more efficient.
Exactly.
Embrace abstract thinking, see how different fields connect,
Mm-hmm.
and never underestimate the power of a well-designed algorithm. Thanks for joining us on this deep dive into the two keys keyboard problem.
Keep coding, keep learning, and keep pushing the limits. See you next time.